Board. Okay, the little red light's on. Okay.
You already told me your grade needs.
Oh, we're getting there. There's a slide. Okay. I haven't said anything to, I told Colt this morning. I got into one of those long semiconductor physics debates with Colt Morris this morning.
Long conversations.
Yes. I miss Colt. He's working here in town.
But how's he doing?
He sounds like he's doing okay. He's still thinking. He's still Colt.
He's still Colt.
Yeah. Most of the conversations I have with Colt are like these mind melds that no one else can understand. So, and they last forever. One time he helped me grade a homework problem in 280, and it took me all day. It took me much longer with Colt's help because he kept on finding reasons why technically the answer was righter than I thought it was. And then we'd sit up on the board and argue about it. And then okay. I miss Colt. Only person who ever took, never mind. Okay, the next big thing that's due is homework 3, and that's due next week. I'm in a good mood. I'm also kind of, yeah, I don't know, reflective right now. Project 2 is due a week from Thursday. Start on it. Draw the timing diagram first. The 3 big things you need to worry about on your timing diagram are the relative timing of equilibration, word line, and the right enable that turns on your digit line inputs and inputs them into the device. If you need help, just Zoom me or during office hours or send me an email. I've decided to have a resume workshop on Monday because what they don't call it career fair anymore. It's like STEM session number 3 or something like that. Turns out to be the real career fair. You got an email about it from Elizabeth Glass, probably today or yesterday. You can search your emails for that. Highly recommend going. This is where companies hire people, start to do screening interviews for internships and for full-time employment if you're graduating. So let's do this, and we'll just do it in my Zoom. I made it 6 p.m. so I have time to go home and chill out a little bit. Yeah, because it's 5:30 is a rush because I don't get out of class until 5:15 every day. My plans for next year. Oh, I was at the same moment, like in this parallel, I was texting you, I was texting Jack, and I told him what I did. He said, "Julie, you're cruel." Like, I only let it last for 20 seconds. Okay. I am no longer going to be teaching full-time in electrical engineering next year. I will be teaching 2 classes. If I have my preference and they do what I want them to do, which they haven't been doing lately, I will be teaching 380 and 490 embedded mixed signal in the fall. No one else can teach embedded mixed signal. So if you sign up for that class, you'll get me probably or a canceled class.
Please tell me Billy's not teaching 280.
Who?
Please tell me Billy's not going to be teaching 280.
I'm not supposed to talk about that. Probably not. Okay.
Is there something going on with him?
Possibly.
He canceled class and lab this week.
Okay. It may be never mind. Okay, I'm going to grad school in applied physics, not sex.
Applied physics, I think, no, it's in CS.
Yeah, it's in the same college. It's not in the same school.
Yeah.
So, I'll be working part-time in Dr. Hambo's lab for the entire school year. I'll be half-time teaching, half-time working in the lab, and the other third half of the time I will be taking classes. Yeah, well, I'm really only planning on taking 2 classes for the fall, but
Is this at NAU or?
Yes, at NAU. This is what I need to do to move forward at this time,
Cool.
because I'm not getting, yeah. Okay, so voltage converters. The voltage pumps. Now we need to generate voltages less than ground, which is the VSS coming into our chip. There's this new signal I'm going to call VBB, which is the body tie for all the NMOS transistors in the 1T, 1C cells. In order to generate that voltage, I'm going to use that charge pump with some latches and buffers and things like that on it. But I'm going to use PMOS only, so I can get the lower voltages. And for my VCCP charge pump, which is going to be a voltage greater than my input voltage of VCC, I'm going to use an NMOS only. These are going to be power supply circuits. Power supply circuits that are basically for, you know, large range across the array. We need to keep the CMOS out of there to prevent the latch up. Remember the NP-NP problem. Anything that generates power, we don't want to have that structure involved because it could potentially burn out and cause destruction to our chip. Now I'm going to reveal the great mystery of why we want to tie the body lower than VSS. This sounds a little funny. Okay, remember the body effect. It's always important.
Always.
Okay, V threshold, the actual threshold voltage, the voltage it takes to turn on the transistor, is a function of VSB, the magnitude of VSB. So VBS, VSB, interchangeable. If we plot V threshold versus VSB, we can see that as the magnitude of the voltage goes up, VSB, we get a higher threshold voltage. Normally a bad thing. If VS increases, we're going to increase the threshold voltage. If VB decreases, we're going to increase the threshold voltage. By making the body voltage less than 0, we have done this. We've decreased VB. We've increased the threshold voltage on all these transistors. Now, why is this a good thing? I remember I've told you all along, I've been saying, okay, and cut off the current 0. And then there's like this side note where I say it's not really 0, but it's a small number and we're not going to worry about it for now.
Very small, unless you're, and
right.
I assume it doesn't particularly matter unless you're doing something very specific.
Right. VDD2. Let's look at the unit cell of this thing. Okay. So this is the 1T, 1C, word line, digit line. We've got a really small capacitor here. So it has a really small amount of charge stored. A small amount of charge either going onto this capacitor or discharging off of this capacitor could make a huge change in voltage. Now, when this transistor is off, ideally the current would be 0, but it's not. The semiconductor physicists have gone through and they figured out, you know, what is the leakage current when this is just like in subthreshold. When VGS is less than VT, what is the current? And this is the equation they came up with. It's derived in a book by Simon C. that is in the other semiconductor class that's taught at the same time in the infinite wisdom of my management. Dr. Chen's class. The 2 classes all year long. They weren't thinking. They never think. They don't know what's going on in the program. Okay, so just yeah, everybody could have done. Okay, but the subthreshold current depends upon a lot of things that are controlled by the process. and like constants of nature that we can't control. And there's this term right here, e to the q times VGS minus VT. If I make VT bigger, this e to a positive number becomes smaller and the subthreshold current decreases. So in order to make this number closer to zero, the actual leakage current, what I'm going to do is I'm going to increase the threshold voltage of these transistors and decrease the leakage current, meaning I can go to smaller and smaller processing, which leads to smaller and smaller capacitors there.
Doesn't that also make it harder to turn the transistors on though?
Yes, it does.
Which means that you use more voltage to generate more heat.
We make VCC, if it gets too bad, we just make VCCP a little higher.
Eventually it'll get like too high. Like that.
Not necessarily, because it's always, the voltage is going to be here is going to be VCCP minus whatever the real threshold voltage is.
Yeah, I think we're dropping in voltage.
Yeah. So that's how they're keeping the leakage current down. But we need another power supply in order to do that. So that's the rest of this. There's not a whole lot left that I really want to talk about. There's a lot of things that I don't want to talk about. Remember this, we talked about this in detail a couple of weeks ago. Basically what I do, the short version, we went through the long-winded version before. I have a clock, I invert the clock, and I use that to switch this capacitor on and off. As I switch the capacitor, I'm getting these voltage spikes across the capacitor that decay away at that point. But these voltage spikes here, because of capacitive coupling into the load capacitor, are actually causing that capacitor to charge slowly over time. Eventually, if we set this up right, we will get a higher voltage there, or whatever voltage, it'll stabilize at whatever our final voltage is. There's a lot of things I can do to refine this, and this is what you're going to see in the next circuitry that I'm going to just kind of skim over. This is a simple voltage pump circuit. This is what potentially shows up on the homework. When I ask you to draw a picture of a simple voltage pump circuit, this is what I mean, not what is about ready to follow.
So you said we're gonna turn, did you say capacitor or the transistor on and off?
We're flipping this voltage on high and low. If this voltage, when this voltage is high, M2 will turn on. This is a diode connected transistor. It should be on when it's low. And so we're charging this node back and forth as we go through there.
So like I don't see where you're pointing, like which voltage.
Oh, okay. So when this voltage is high, this transistor turns on, and this transistor, this transistor, okay, is diode connected, so it's going to, as that's high and that's high, VGS, this one might turn offish. It's going to turn more towards off. And we're using the gate to source capacitances in there to to couple the charge from this capacitor is going into the gate to source capacitance here, which is going to be coupled into the gate to drain capacitance here, which is going to charge this load capacitance.
Okay, so when C1 is high,
Mm-hmm.
then M2 turns on, and
Right.
We get that waveform up top.
Right.
But then,
Well, we don't get, when it's high, this is charging up here.
okay,
When it switches back, and then it starts to discharge, that high voltage that we've charged this capacitor up to starts to discharge through this capacitance.
okay.
And as it discharges through the gate to source of M2 and the gate to drain of M2, it charges C load,
Okay, so then the wave on
right?
that C load is, that
Right.
is the ground.
This is always above 0 volts. And because it's always above 0 volts, it can always charge C load. And so it's just continually charging C load until it reaches its maximum value. Okay.
Why wouldn't we just want to use like a boost converter or something?
This,
Or
oh,
is this the same thing?
okay. The problem with a standard boost converter like you'd see in Dr. Yaramasu's class is it has this really annoying piece on there called an inductor.
Oh, that's too big.
You can't build an inductor inside an integrated circuit. Well, you can now. It's called MRAM. But it takes a special magnetics processing above the CMOS front end to put an inductor in. So you're adding a whole layer of processing to put inductors in.
So you can't put an inductor in the
You do not put inductors in CMOS devices. You can sort of do a little bit of inductance. Remember from EMAG, or not,
Is it because of the magnetic field of the inductor?
yeah. A wire acts like an inductor because a wire generates a magnetic field around it according to the right-hand rule. So if you have current going through a wire, you're going to have a magnetic field around that wire going in the way your fingers point. If your thumb points in the direction of current flow, your fingers are the direction of magnetic field.
Oh, wow.
Okay.
That is actually a better explanation right-hand rule that I ever got than I ever got in physics.
Right.
That was a better explanation.
There was an original plan to this next year where I'm teaching physics instead of electrical engineering to just pull me completely out of 6.
I'd love to take a physics. That'd be great.
Gabe was really excited about me teaching the electronics for physicists.
Ooh, good.
Do you want to stick around for that?
I kind of want to. I kind of want to. Wait, I don't know. I've already taken that class, I think.
Okay, from Buzz?
Yeah, to Buzz.
Okay.
I just Buzz. You were fine.
Yeah, I know. And then that's why I'm like, as soon as he saw it, it's like replacement Buzz. Okay.
Better than Fobar teaching.
Okay, I don't know who Fobar is.
Fobar teaches all of physics too.
Okay. Oh, and I can also teach physics too,
You'd be better than Fobar.
because I've taught 280 forever. Okay.
It's more 188, I think.
Oh, okay. Well, well, maybe it's physics 3 that's 280-ish.
Physics 3 is optics.
There was another one a few years back that was exactly like 280. I mean, it was almost like a duplicate. Only the currents were going in the wrong direction.
Oh, yeah, I know that class. Yeah.
Okay.
I think it's electronics too.
Okay. So this is the pump we're going to put on VCCP. We're not going to spend a lot of time on this. You can kind of recognize some of the pieces. It's the same idea. I have the clock coming in here, and all this piece is a latch for the clock. And all this piece is another latch for the clock. Yes. Well, I don't know if it's bigger. I don't know what the relative sizes of them are. It's more spread out, but we have a second latch on there. We're inverting it. Here we have the C1. It's showing up again. So the C1 is charging. The charge on it stays positive, and it's charging up the output through some magic through the rest of the stuff. Okay, VCCP, we're using all PMOS all NMOS transistors to avoid the latch-up problem if I tried to use CMOS on the output stage. Okay, we'll talk about latch-up more later. The VBB pump, same idea. It's basically the same circuit, but a few more inverters in there. And we're using all, I doubt this circuit is what they're actually using now. So it's just not, and it's basically just to get VBB out.
What
If
is
you're-
the addition of the latch? What does that like do?
The latch just basically stores the clock into it and gives you, instead of draining the power to charge these capacitors off the clock directly, you've got a buffer between the clock. So now the power to charge up these capacitors is coming off the latched value. It's just a way of storing that clock value.
Okay.
VBA is less than that.
Yes.
Is it tied to the P file of the transistor?
Yeah, it's coming off of the PMOS transistors. We don't want to use CMOS because of latch up. Okay.
Don't use a smoke with latch up. And wait, why is VBB less than ground?
VBB is it's the body tie. We want to make the body tie lower to give us a big VBS so we can lower the leakage current on those in-bit transistors.
Okay.
Leakage in small devices is got, oh, well, let me tell you, this, you'll get this. Well, we should have gotten this like in 380 when Dr. Campbell came in. The story of leakage current. As transistors got small, okay, back in the day, we have like a 1 micrometer transistor. As the transistors got smaller and smaller down to maybe about 20 nanometers, the leakage current kept going up. And it was getting to be a big problem. You could never really turn transistors off, and you always had some current going through your CMOS devices, so there's always more heat generated. About the 2015 nanometer days, Samsung came up with this idea for using FinFETs. And when they used FinFETs, the transistors there was a big back off on that. The leakage current suddenly dropped down going from FinFETs to planar transistors. And they were so much better, and they had better output resistance too, that everybody jumped on the FinFET bandwagon. There was another technology they used to get down to 10 nanometers, an alternative technology called fully depleted SOI. And that was basically, they put an insulating layer in the substrate. You need to keep the substrate yay big, not that big, but maybe like a millimeter thick or something like that, so that the die have enough mechanical stability they don't shatter all the time. But if you put a layer of silicon oxide really close to the edge where you put those transistors, you have an insulating layer, and now electrons can't move through the bulk of the substrate. What's through an oxide? It's a relatively thick oxide.
Okay, so that actually.
It prevents things going through it, electrons, holes, and everything. That worked down to about 10 nanometers, and going from 10 nanometers to 5 nanometers, what they had to do in order to get there was they had to use FinFETs on fully depleted SOI. They had to use both technologies together. And the processing technology is getting so complicated. There's really only 2 companies that are really hitting the bleeding edge right now, and that's Samsung and TSMC. And TSMC is building a big fab down in, no, it's not in Chandler. It's, no. What? I saw where they bought the land. It is on the northwest side of Phoenix. Yes. They bought like 1,200 acres. They're planning on making this thing bigger than Intel eventually. And
Well, I guess I'll
Okay.
tell Campbell it's not Campbell.
okay. Yeah, because I mean, I saw that I went to like a TSMC meeting like about a week ago,
Huh.
and that's where they bought the land.
Yeah, you were talking about that.
Yeah.
Are we gonna have someone talking about
No, don't get me started. Okay, they're not coming. They're still hiring people. They've the plan is they wanted to hire like 300 people by 300 new grads and like 1,000 people or something like that by spring. They've hired about 200 of them, but there'll be more hiring as the years go on, especially with 1,200 acres to fill with engineers.
Yeah, that's a lot of space for engineers.
Yes, it is. The other company, Intel, was keeping up with Samsung and TSMC for a really long time. They've fallen behind. Intel's having a harder and harder time hitting their target dates, and they're like hoping to do like 8 nanometers or something like that.
They're slowly becoming less relevant.
Well, Intel can still design processors, but what may happen, it may become like a partnership that AMD has with TSMC, where AMD does the design and they get them built by TSMC. And Intel may be heading that way fairly shortly too.
And, what was it, when the Micron guys came last time, they were talking about how their contract with Apple,
Mm-hmm.
Apple has recently decided to manufacture them, their things themselves rather than have Micron do it.
Okay.
Apple's moving over to their own proprietary
Uh-huh. But Micron usually just builds the memories, not the processors.
Yeah.
Yeah. Okay, this is a ring oscillator.
Oh, yeah.
Who's in 638?
639.
639. Oh, yeah, it's spring.
Yeah.
Okay, so there's a couple of people here in 639. Nobody on Zoom raised your hand, so I'll just run with this. 2 out of 3 people in the class are in 639. You've seen this ring oscillator circuit before. The basic thing here is I have an odd number of inversions. The reason why, another way to do this would be to make one inverter that's really small. Each one of these gates, each one of these inverters gives you a little bit of delay. So what you want to do here is you want to take your input, invert it an odd number of times, and feed that back to the input, which causes the input to change state, and it inverts, and it takes a while to get back through. And you can actually build a square wave generator like this.
The jelly beans are single input muxes, right?
Yes, the jelly beans are single input muxes. So they're just basically buffers. You can enable it and disable it with power up and whatever this other signal is over here. What?
Any single input muxes?
It's called a tri-state buffer.
Yeah, we use tri-state buffers. I can borrow.
We probably have tri-state inverters. And if you take an inverter and put it in series with a tri-state inverter, you have a tri-state buffer.
Okay.
Yeah, two inverters make a buffer. Lots of problems actually building this. People try to use this as a puff, if you know what I'm talking about. That's the big, you can use it to build a square wave generator. Also, the timing isn't really reliable because every time you build this circuit, these why can't I write? Okay, I'm not in between slides. Oh, maybe I have to do this. Draw. Sometimes that works.
The pencil's twitched.
The pencils twitch, yeah. So, okay, I can't draw.
A little side note and say that this is what you do in Minecraft when you need a clock.
Okay, I can draw with my finger. Yeah, this is what you do in Minecraft when you need a clock. The thing that why people thought this would make a good puff is because if I build 2 of these, the delays on the inverters are never exactly the same. And I can use the inverter delays as a generation of a puff. It doesn't work really well in practice. If you're in 639, this isn't a good thing to pursue for your projects. There's better things.
I want to just build one.
Okay. Want to build a DRAM hub?
Can
Yeah,
I can tell.
I can tell you the secret.
Oh, I love it.
I need the secret. I don't have the project.
If you can write to the DRAM memory on a FPGA board, there's a way to do it fairly easily if you read the manual. You have to actually break out the big manual. Jack knows how to do it. And write all ones into your DRAM. And then you turn the power off and wait. You probably have to wait at least 30 seconds or so, and then turn it back on and read it out. You will get puffiness.
Yeah. And Bo briefly went over that as well.
Oh, you did. That was entirely it was my idea, and Jack implemented it.
Like, I don't know. I want to.
Okay, you have to be able to write to the hard part was for most people who couldn't do, the people who couldn't do that, was writing to the memory.
Okay, but
if you can write all ones into the memory and read it, if you can interface to the memory on the SVRAM on the Quartus board, then you can do it.
okay.
Yeah.
I might have just reading, but I think I
Okay.
may figure it
And you may just talk to Jack too. That might, yeah. If Jack will, if you can get it out of Jack.
out. He's not still mad at me. I don't think he's mad at me still.
I don't think he's mad at you. He was mad at me for teasing you a little bit yesterday. Okay. This inverter with the funny little thing in it is called, I recognize that symbol.
My glasses.
Okay, it's called a Schmidt trigger, named after someone who's named Schmidt. And he came up with this idea. It's a inverter with hysteresis. And when Dr. Campbell comes in here and starts talking about ReRAM and MRAM, there's going to be a whole bunch of hysteresis curves on the board. Basically, all hysteresis is, if my input is high and I want to switch it low, it's going to take a higher voltage on the input to turn it on low, and it takes a lower voltage on the input to turn it high. So you have to pull the voltage down further in order for it to change. Now here, and you can build oscillators out of these things amazingly easily. Come to my office if you want to hear about that, or just come talk to me. Okay, this is the problem when my circuit doesn't have hysteresis. I have a signal that's messy and looks like a real world signal. When my input starts to go below, if I have a single threshold, and this is, oh great, this is the single threshold right there, 2.5 volts. As soon as my input goes below 2.5 volts, the output of the inverter goes high. Well, that's fine, but because there's noise on this signal, a little bit of time later, my input goes above 2.5 volts, and it says, oh, I need to go, since my input's high, my output needs to go low, and I get this small little timing problem, and that's called a glitch. And if you ever want to waste weeks of your time, well, it's not really a waste, but this is beating down glitches in a digital circuit will just can drive you batty. These little timing glitches can cause your whole circuit not to work.
It's supposed to be spiking downward, but because the glitch it spikes upward. It
goes above that single threshold. Yeah. Now, if I have two thresholds, if I use hysteresis and I need at least 2.5 volts in order for it to switch. It needs to go above 2.5 volts to switch high, but it needs to go below 2 volts in order to switch low. Then I need to have spikes that are bigger than a volt to actually create one of these glitches. That doesn't happen most of the time, and you get a cleaner output. The ReRAM curves look like hysteresis curves. And we'll be talking about ReRAM and NRAM a little later in the course. And after I wrap up my piece of that, then Dr. Camp, that means I have to be somewhere in a half an hour.
I'm sorry, I didn't notification. What is that?
Oh, no, no, that's okay. That's all right. Yeah. Yeah. That's my, you've completely forgotten the meeting buzzer, but I didn't. Okay, so this hysteresis gets used all over the place. This is a regulator with hysteresis. You get hysteresis through feedback. And again, I'm not a regulator designer. We just don't really want to talk about that here. Okay. This is a simple DVC2 generator. When the homework, if I ask you to draw a simple DVC2 generator, I don't want to see the next slide, which looks like this. I want you to see this slide.
And that was on pre-lecture, like two pre-lectures ago.
Okay, good. It shows up on the homework at some point. All this circuit is an inverter with its output tied to its input.
Wait. Wait. You're not kidding, are you?
I'm not kidding. It's an inverter. Look at the circuit. This is an inverter.
Yeah.
There's a PMOS transistor. There's an NMOS transistor.
And it's tied to each other.
And the output is what we call VCC/2, and the input is tied to the output.
I'm a little upset.
Okay, what this does, remember the inverter voltage transfer curve looks something like this. There's only one stable operating point of that circuit, and that is right here at VM, where both the input and the output equal each other, because the input and the output have to equal each other because they're tied together.
Yes. Yes, they.
Okay. Everybody okay with that one? And you have to power this up to make it work.
Is it giving us BCC/2 or DVC/2?
Well, okay, remember we can't use that slash.
Right.
Okay, there are two power supplies in the chip that are powered at VCC/2. The one that we've been using for the project is called VCC2, and that's the bottom plate of the capacitor in the 1T1C. There's another, and we keep these power supplies separate. The other power supply that's powered at VCC/2 is the one that powers the equilibration circuit that equilibrates the digit lines. So when you equilibrate the digit, and for your project, they're tied together and we don't care. But normally in the chip, we want to run the bottom plate of the capacitors off a different power supply, even if it's at the same voltage, than the equilibration to prevent crosstalk between the two.
Oh.
Okay.
Is it important that the NMOS and PMOS have the same resistance?
Yeah, you would, in order to get VM right in about the midpoint range. If the PMOS had a higher resistance, if you made them the same size, then it would move this point like up and down the curve. If one of them's different, it's going to move that point around this. I'd have to think about it a minute to figure out which way it would, a bigger PMOS would move it. Mm-hmm. So you want to keep the PMOS 2.5 to 2.5 times bigger, and simulate it for your process to make sure that they have the actual same resistance. Now DVC, oh, what the answer to Zach's question was DVC2 is the power supply that powers the digit lines when we equilibrate it to VCC over 2. I have to give it a different name because it's coming from a different source.
The other daily wire, you had us always make POS two times.
Right. Okay, we're almost done with this. This is the more elaborate version of this. It's got an enable. It does. And it has, oh, a bunch of transistors with long L's. Long L's give you higher resistance. And maybe that's if you have a, I don't know.
It's the other one's so simple. This is
Well, this is how it works really. When you're working is, or when you're working with Dr. Cambo too, is you go into his office and he draws a sketch like this on his whiteboard and says, this is the idea, this is what we need to do. And then you go, oh yeah, that's simple. And then you have to go out in the lab and implement it. And you realize that it's not quite as simple as you originally thought. I'm going to have to do things like make the input stage have a higher resistance, which is the reason for these long L's. I'm going to need a bigger driver here in order to actually get the output current that I need to drive the digital lines. I may need to enable it, and you just start adding to the circuitry and it all gets kind of pieced together. 4 years ago, 4 years ago, Dr. Cambo drew a current mirror on his whiteboard and said, see, it's simple to match the current. And I go, yes. And 4 years, we still haven't been able to do this yet because he didn't really specify the requirements. And this is what the things that makes it hard. We found ways to work around having to do this instead. Is that he wants the current to be stable no matter what the output resistance is. And the output resistance, he won't give me a spec on it. It can vary between a k ohm and hundreds of mega ohms. And that just changes how the circuit works completely. And he wants 100 nanoamps plus or minus 0.5 nanoamps. It's harder than it sounds. About once a year, it becomes really important and it becomes a priority and we start working on it and we make some progress. And a week or two later, it becomes a non-priority again. And so it's just been this. It's the real world. Everything's like this. I'm not complaining about Bertrand. I'm telling you the whole world's like this.
Yeah.
I built this last summer. I built this beautiful ternary comparator, and nobody even knew what a ternary comparator was. I made up the function and then just built it. And there's been a grad student working on it for 3 or 4 months, and now we have a problem. And the ternary comparator has been pushed to the side while we fix this other problem, and then it'll come back better than ever. Yes. Note to future self. This is the Bill and Ted.
Yes.
You probably started this. This is when I look at my slides on Tuesday. I'll say, oh, wait, I didn't start this, and I'd start it all over again without that little note. Oh, good. We're into RF stuff. So we're going to talk about transmission lines, stuff you should have learned in 364, and how it applies to the real world. We'll talk about impedance control, and we'll get through some of this. Oh, and ESD, an amazing, and ground loops, otherwise known as SRPS, signal return path shift, or as I call them, ground loops or ground impedance.
I read that in the book last night, and I didn't actually draw on the fact that it was a ground loop.
You can make ground loops out of these things once you have impedance in there. Okay, so the output driver. This is when we go to the pads of the IC that have to connect to the pins to the outside world, how fast that driver goes has a significant impact on the user perceived speed of the chip. And it's operating in a really tough environment. You don't know what the PCB designer has done. There may be problems with ESD. You can't control anything that's tied to the external world. A small voltage of like 50 volts that you can't even feel may be enough to damage it. So I'm going to need to put some ESD protection on the output driver, and that will show up in the next week or two. We'll look at those ESD protection circuits.
South North Campus with
Yeah. Yeah, cotton pants, bad for ESD. Wool socks, I always wear wool socks. A bad idea. All kinds of things like that. We're going to talk about the transmission line issues, some parasitics, because there's a couple of things that are going to affect your output. First of all, you have to drive the pin, and the pin is large enough and the frequencies are high enough that it's got parasitic capacitance and inductance that will affect your signal. The PCB traces are going to be acting like transmission lines when you get to 2 gigahertz. So high-speed signals, you've got to worry about some of these things and matching the impedances. Now you could write this really detailed spec for the printed circuit board designer saying, this is what I want the transmission lines from your chip to look like. But no one's going to read it. And very few people are going to follow it. And you don't want to make it too hard for the users to use your chip. So the idea kind of evolved that maybe I can take that output pad and put some circuitry on it that will auto-tune the characteristic impedance of my output pad based upon what it's hooked to. So now I don't have to be so amazingly specific with the printed circuit board driver designer. I can make it easier to use. Now this is the idea. Digital signals, I create them and they look beautiful, and then I run them through something that has an RC delay. And as soon as I run them through something that has an RC delay, you start to see charging and discharging time constants. Another issue that comes up is I make another equally perfect signal and I run it through a transmission line that's mismatched to my output driver. You see reflections, so you don't get the perfect power transfer to the load. The power that's not transferred to the load actually gets reflected at the load and goes back into your signal and starts distorting it. So these little blips right here are caused by reflections on the line and mismatched impedances. You can never match them perfectly, and all signals kind of look like some version combination of these two things. Now, in order to determine whether my signal matching is good enough and whether I'm doing it well enough, they came up with this concept of eye diagrams. The people at Micron were really amazed when my students came in and saw this on some guy's scope, and they thought it was a trick question. And they said, "Do you students know what this is?" And like in unison, they go, "It's an eye diagram." It was great. I was really proud of them at that moment. Okay, so what happens here is what I'm doing is I'm triggering my oscilloscope off of the clock edge. Sometimes it's a low signal going high, sometimes it's a high signal going low. And I have a storage scope, so it repeatedly triggers off the clock edge and generates a family of these curves. You can see here that these aren't perfectly matched in time. There's some jitter in time in there. But they're fairly, this is an amazingly good eye diagram. They're fairly well matched. The difference in time in there is what we call jitter. It's a technical term. We use it a lot. You can see a little bit of jitter right here, a little bit more jitter on the rising edge than on the falling edges. The goal of these eye diagrams and what they consider to be a good eye diagram is you want the transition times going high to low and going low to high to be about the same, which opens up this area. No, it's just not. Where am I? Jitter is a technical term. Okay, so we want to open. Sorry. Like, oh, there we go. Okay. You want to open up that eye diagram as much as you possibly can. And that means if it's open, these times here, the rise time and the fall time of those signals are fairly evenly matched, and there's not a lot of garbage in there. And you've got the high level and the low level are relatively matched. We'll look at some bad ones in a minute. We'll see how bad this gets. I've seen some horrible ones too on people's benches. Right. Why am I, okay, I don't get to talk about eye diagrams yet. We're going to talk about, we're going to go back to transmission lines and how they affect these eye diagrams. The issues we've talked about, the IC, the package, the PCB, and the backplane. You may not know what a backplane is yet, but you've seen one. If you open up the inside of a computer, you've got a motherboard that slides into a slot somewhere with pins. And then like that motherboard, so it slides into a slot with pins, and then it's connected to maybe like the memory card through this other printed circuit board on the backplane. So as you slide into those, the motherboard into those slots, the connections that need to go to memory will be routed up the backplane into another memory slot that will go to your SSD drive or something like that. If you're looking like at a big tower computer.
Yeah, it's the secondary circuit board.
Yeah. You're sliding circuit boards into connectors that tie to other circuit boards. The circuit board that everything's connected to is called the backplane, is the general term for that. Backplane design's a whole nother pain in the backside. Okay, at high speeds, all of these connections are going to act like transmission lines, and it's not letting me draw again. I just touch it a few times and it kind of like magically comes back sometimes. Or not. Okay, so all of those are going to act like transmission lines. This is the basic transmission line model you should remember from 364. You have a resistor, you have a
It's always something.
It's always something. There's always some technology crash. Okay, you have a, I'm going to use my finger. You have a resistor in series with an inductor. You have parallel resistance or conductance, and you have a parallel capacitance. You make these differentially small and you integrate along the line. Now, this is not resistance. This is an AC resistance. It's a characteristic impedance. And by characteristic impedance, it is VAC over IAC. And that is, I'm sorry, this is my finger painting.
Different resistance.
This is called Z naught. Oh, sometimes it works. Okay, I got a, okay, Ohm's law, AC.
Ohm's law, AC edition.
Okay, so the resistance of this line is fairly small, but the ratio of the AC current on the line to the the AC voltage on the line to the AC current on the line is this thing called characteristic impedance. Guess what? I can draw again. Okay. And for a lossless transmission line, R is small, the resistance is small, G is big, so it's a big parallel thing, so it goes away. The Z naught reduces to the square root of L over C. I want to match this AC impedance to whatever my load and source is to get max power transfer. If I don't match, well, the next slide's about matching, so I'm going to just flip to the next slide. Yeah, there's a note to myself on the slide. I have the source here. Ideally, I would want Z naught to equal the load impedance, and that gives you max power transfer, or the conjugate of each other. In the real world, this doesn't happen. If my source, my driver, has an output impedance of 18 ohms, and I want to match it to a transmission line of 63 ohms, what I could do is take the driver and put a series resistance in there, and now I have a Z naught of 63 ohms. This statement right here is to tell me not to talk about quarter wave transformers. If you were dealing with microwave frequencies where the length of this connection here was long enough that it affected the characteristic impedance, the normal way to do this would be to make this 33.7 ohms. You use the geometric mean of these two and you do a quarter wave transformer in there. Every time I looked at the slide, I would just assume that, never mind. That note's for me. And that's part of that stuff. Okay, what I'm going to do here, now I've got an output driver. It's got some Z naught. I've got my DQ pin going out to the outside world. It has some ZL, and I want to match those. I have no control over ZL. What I can do is on the die, internal to the chip, I have this transistor right here that I have an ODT pin that controls whether these transistors are turned on or not. If they're turned on, I now have a resistive divider right here that is in parallel with this that helps us match ZL. Now, I've already said the ZL is going to be variable and I have no control over it. It worked fairly well when people could follow the rules. And that meant that the printed circuit board designer was looking at the specifications of the IC to see what impedance they had to match to it. They came up with families of specifications that people would follow. It was like, in general, if you're designing a printed circuit board and you're using chips, if they're all following the same specification, then you want your transmission line impedances on the PCB to match those specifications. That works fairly well, and now we're in the Wild West where 1.2 logic, 3.3 logic, all on the same board, and you can't, and different bus standards on the same board, you can't get away with this anymore. We'll get to a solution for this. And this is the idea I have. When I'm writing to it, I'm going to choose whether I put this termination on there or not to improve my signal coming in. I can choose whether to put this termination on there or not to improve my signal going out. Okay. Nowadays, we're in the wild, we are really in the Wild West. It's bad.
Is that stuff censored?
Is that censor?
What is happening?
It's things Dr. Brower didn't want you to see. I don't know. It's irrelevant to this argument. Now, if I want to do this so I can match my IC output impedance on the fly to whatever's on the package or on the printed circuit board, I can do this. I have up to 10 minutes. Okay. I have these various size transistors here. Times 16, times 8, times 4, times 2, and my base size. They are all a multiple of 2 bigger than each other. The resistance of that channel, remember from somewhere in 380? Great, that did that thing again. RDS is proportional to 1 over W over L. So if I make W bigger, if I make the W over L bigger, I'm gonna make RDS smaller. I hate technology. So this X16 transistor has a big W over L, so this is gonna have the smallest R. This one is gonna have the biggest R. And they're that's times 1. They're binarily weighted. So I could choose a pattern by controlling the VO high 4 to 0 bus. I could choose a pattern of having some transistors on and some transistors off. The total resistance is going to be the parallel combination of all the resistors. And I can tune this to make the best match to the pin. And I can do this every time I power up. In case somebody decides to pull an IC out of a socket and solder it down to a printed circuit board, the characteristic impedance changes. What I want to do is have some kind of feedback in here where I see how much voltage I get on the input line versus the matching, and I can vary these until I get the highest signal right here. I'm doing matching on the fly. This RPU, the parallel resistance, I want to make it bigger than I want to make it much bigger than the biggest resistance here, so that it gives me a base resistance, a maximum value of resistance I can have here. I don't want it to be open circuited. So I'm going to make it bigger than any of the individual pieces. Okay, now that's where I was at. So how do I do this? I've got a simple controller circuit here. Basically, I've got these binarily weighted, this shows up on the homework, I'm sure. I got these binary, not this particular one, but the idea. And what I'm going to do, and you may have talked about this in 286 and 380 in our ADC and DAC days. We've got an up-down counter. I'm looking at my pad. I've got some external load impedance I can't control. And I'm comparing the signal on this to some voltage Vref. And I want the signal coming into my circuit to be at least Vref when it's high. I compare this, I change the values, which transistors are turned on, so I change the impedance load, and I see at what point, as I'm counting from zero to a high number, what point do I actually trip this and get my output voltage, or my voltage coming into this pad, into the IC, up to an acceptable level. And that is the point I'm going to call, this is good, it's matched. It's not a perfect match, but at least guarantees that enough signal from this line is getting into the chip that I can do a digital read on it. And these could be like 2 gigahertz, 10 gigahertz digital signals. They're fast. And now the right diagrams come up. These are not, I have a hard time, I really do, saying which one's better. Part of my problem is the scales look different. Yeah, these are kind of hard to see. Let's find a bad one. Okay, so some of this was in your reading for pre-lecture 12. Have you gotten that far?
11 was used.
11 was due today? Okay, so this is in your, the stuff that we're talking about today will be in your pre-lecture for next class. What? Yes, and there's a whole like folder full of little reading assignments. What we want to be able to do, they've got 4, this is where they started out. They had 4 basic standards. And this was telling people with 3.3 volt logic, there were 2 standards. One was 50 ohms and one was 25 ohms. And it was up to the printed circuit board designer and the system designer to make sure the impedances matched across the entire system. And you had to follow these standards. And this is the eye diagram, and we talked about that. Which is better? The one with the bigger eye. Let's look at the next one because that one is more obvious. Which one of these is better? Thing 1 or thing 2?
One of the left has some character.
Yes, it does.
It's very exciting.
It is.
It's
It's disturbing. The one on the SSTL one is kind of disturbing, and that basically what I'm doing. Remember, I'm triggering the clock on the same location, maybe somewhere about here, and no, the clock's triggering over here. It's an epileptic. Sometimes it takes. There's situations where I get a much longer delay. You probably do this like thousands of times. Sometimes my input signal coming in is not very good. It's a different voltage than it is there. This is a much cleaner eye diagram. This is only at megahertz. This is like a 0.5 gigahertz right here. We have 4 minutes left. Okay, so we don't have time to do that. Let's pick up here. I want to go through this because it shows up again on the homework, and you're going to have to do some calculations based upon this. You're actually going to have to generate a spreadsheet is the idea, because if you have 1, 2, 3, 4, 5 things, there are 32 possible combinations of each one of those bits being on or off.
Are these 2?
Right, 2 to the 5th is 32. 32 combinations. Each one of those combinations, I ask you to calculate what the parallel resistance is. It's fairly easy to do in Excel if you know how to write formulas in Excel. If you try to do this by hand, you're going to have 2 pages of calculations to do. So yeah, we'll talk about that next class. And it's time to go to 380. My son is, I gotta tell you, his first thing was, so you really think you're gonna get more respect as a grad student? And I'm like, yes, it's that bad. Okay, I should stop recording.